All right, recording's rolling. It's Friday, January 20th. So I think about half this class is seniors. They're doing a senior panoramic starting about now. So and then there's club photos throughout the day. So if you're in a club, you probably know what time you're supposed to be there. I do songwriting club. That's at 12:45. I think a few guys have showed up. So if you want 12:45, show up to that one. You can. In this class, we're going to do midterm solutions. You guys got the midterm on your desk. Now, of course, I'm recording this. I'm going to post this to Google Classroom just like I do every day. But if you're a senior, about half the class of seniors, you probably want to go ahead and go over to the gym, get the senior panoramic, and then, of course, I'll post this video, and then you can see any of those solutions, right? So all the seniors, I think about half you guys are seniors. Well, maybe less than half. Really, we just got a few. Actually, we just did have a few. Oh, all right, yeah, checking this out. Oh, all right. Looks like we didn't have as many seniors as I thought we did. All right, so we got looks like Rick, Michael, Leo, Studi, Iska, Ryan. Okay. All right, so all you guys, all right. All right, so midterm. All right, there were think about like 5 or 6 of you that got every single one of these problems right, and then a few more of you guys that only missed one. So if you're in that camp, then I put a book on your desk in case you get more out of that today. But rest of you guys, yeah, like all these problems, all 10 of these, I think you guys should definitely be able to do. So missed any of these, we'll go over the solutions right now. Okay, number 51. Right, you guys remember each of these was worth 5 points. So there's 10 questions I'd like to go over today, and then this was worth that. Well, half your midterm. The other half was just multiple choice, like conceptual questions worth a point each. All right, so here's the 5 pointers, the big ones. Okay, graph shows ball thrown straight upward at the edge of a cliff. All right, this is a velocity versus time graph. So we're gonna take a ball, throw it straight up. Right, and suppose you have a radar gun pointed at it, and like every single second or tenth of a second, you grab its speed, and then you plot it.
Good morning, Sierra. Happy Friday. We are coming to you live from guidance where Miss Diedrich and Miss Ramsey are our talk of the week.
All right, recording is resumed. All right, so throw the ball straight up from the edge of the cliff, looking at velocity versus time. Hey, well, why is this velocity sometimes negative and sometimes positive? Like, what's going on right at the zero velocity mark?
Going backwards. It's a turning.
Yeah, it's like turn around, right? So in terms of the location, the ball is at its maximum height right there, right? Yeah, right. Okay, so let's get you know what? Let's do all 3 graphs for this one. We get got a ruler here. All 3 classic kinematic graphs. So distance in meters versus time in seconds. Velocity, I should say displacement in meters versus time in seconds. Velocity, meters per second, time in seconds. So the acceleration, meters per second squared versus time in seconds. Right, you guys are taking notes, especially if you didn't get these. Okay. So the one I gave you looks like this. Right, and I was defining which way is positive, up or down, according to this graph. Down is positive, right? Because gravity is pulling that way, and it eventually tends towards that way. Okay, so down is positive. Okay. Here's the peak. Okay. What does acceleration versus time look like for this graph?
Maybe constant.
Yeah, constant. Boom. Right. Should be about 10 meters per second squared if you're on Earth, and then also it's the slope of this line, right? Isn't the slope of this line also equal to acceleration due to gravity? Okay. Which should have been, I think it is 10 meters per second squared, right? Yeah, look at that. Okay. Up 10 over 1, up 10 meters per second per passing second. All right, how about the tricky one? Now, if the top of the cliff is 0.0, right? Then what's the rest of that graph look like? Can you guys draw it before I do? There's something special going on here. So you guys think, okay, well, there's the peak there. Let's see, up is the negative direction, down is positive. Something like that, right? You guys get that? Okay. Right, now, everybody's numbers are different. I don't know if your numbers are exactly this, but mine says it takes a second to reach the peak. So take another second to go back down to the top of the cliff. And then from there on, it's on the move. Right? So it can be a parabola shape, right? Right, so the question is, what is the height of the cliff? Now, this I remember when I was doing the midterm review with you guys, I actually threw this question to you guys, and Elijah told everybody that the way you get the height of the cliff is to do what?
The area under the.
Yeah, it's area under the graph, right? And then has something to do with displacement. Now, this big triangle represents the distance from here to, well, I guess like bottom of the cliff or wherever the graph ends, right? And the little triangle represents the distance from where you threw it top of the cliff to where its maximum height. Right? This is kind of like its height versus time just upside down. Like I said. Okay. And so if you subtract the two, the big triangle minus the little triangle, that will tell you the height of the cliff. Right? Or another way to think of it is going up and going down, that cancels out, that's a wash, and you got a trapezoid left over. And that trapezoid also represents the height of the cliff. Right? And so we definitely went over that one for during the review. And so you should be able to look at that and make sense of that. Okay, yeah. And so let's do the numbers. I'll do the numbers for this paper in front of me. Let me zoom in. Again, your numbers might be different, but graph shape's the same. Okay. So big triangle, 1/2 base height. So base of 3 seconds, a height of that's 30 meters per second. So 3 times 30 divided by 2. 3 times 30 divided by 2, right? So from its peak down to the valley floor, right, that's going to be 45 meters. Now, that's not the answer quite yet, though, right? Because from the top of the cliff up to that point, that's 1 times 10 divided by 2, that's 5 meters right there, right? You guys see a 5-meter triangle on my paper, right? So what's 45 meters minus 5 meters? 40 meters. Bam, which is the answer right there. Okay. All right, you guys can figure out what parts of the triangle correspond to what. So the slope is the acceleration. The area of the curve has something to do with just displacement. Different areas represent different displacements. Okay, number 52. We got a projectile problem. Cannon, top of a cliff, just aim straight horizontal. And I told you the height of the cliff, where the cannonball lands, where it's going to go to a parabola shape, right? Bam, projectile, classic projectile. And let's use gravity field as 10 meters per second squared. And what was the blast speed of the cannon? Because right? If it's not a very good cannon, it's like the cannonball is not going to go very far. If it's like blast really hard, it's going to go a long way. Right? So for these parameters, these numbers, right, there's some associated blast speed. Right? Well, projectiles, you guys know there's vertical motion going on, there's horizontal motion going on. You got to keep those separate. The thing that ties them together would be like the amount of time it takes to cross, the amount of time it takes to fall at the same time. But everything else is different. Displacement, horizontal, vertical, that's different. Acceleration, there's no acceleration horizontally, all the acceleration is vertical. Speeds or velocities are separate, horizontal and vertical. Okay? Sometimes here I gave you guys a framework for this. That there's what's going on horizontal, there's what's going on vertical. Right? Horizontally, it's just x, v, and t. Maybe we'll put a little subscript x on that v. It's like x direction. Okay? But in the vertical direction, it's a bit more complicated. You got tax vv, right? Time, acceleration. So instead of acceleration, maybe I'll say g for gravity field because that is the acceleration. Instead of x, I'll say y, or you can say h. Okay? So v naught y and v f y, right? There's a lot more about because if it's accelerating, got to change velocity. Not here, but here. Right? Right. So I told you a 45-meter tall cliff. There's 45 meters. The cannonball lands 544 meters across. 544 meters across. Right? And you guys know gravity field is 10 meters per second squared down. Oops, forgot my unit here. Meters. Right? Okay, so that's what I explicitly gave you. Okay? Now the fact that the cannonball is aimed straight horizontally means you also know what?
The initial vertical velocity.
Boom! Initial vertical velocity, which is equal to
0.
0. 0 meters per second. So when that cannonball is leaving that cannon, it's not moving up or down for the first nanosecond. Okay? Now after that it starts, of course, moving down, but right? You guys hear why that's 0? Right? I did not explicitly tell you that. You'd have to know that based on the fact that cannon things horizontal. Right? All right, you guys see a bunch of information here. You guys could calculate the amount of time that it takes to reach the valley floor, the amount of time. What formula is going to get you there? Y equals 1/2 gt squared. okay, which is a simplified version of, I think, x equals x naught plus v naught t plus half at squared. You can kind of boil it down to this with this going on, right? Okay. All right, so we know it's going to fall 45 meters in Earth gravity. This is my numbers. Your numbers might be different on your paper, but it's the same procedure. Right? So with my numbers, how much time does it take to fall 45 meters on Earth? 3 seconds, right? 3 seconds, right? There's a table back there, by that wall hanging from the ceiling. Right? Yeah, you guys remember? 3 seconds. 3 squared, 45 times 5, 45 meters. Takes 3 seconds. 3 seconds to fall 45 meters on Earth. Right? That's always been true. Right? You guys see this like many, many times in this class, right? Right. Now, so if it went 544 meters in 3 seconds, x equals dt, or if you like, v equals x over t. Okay. Went 544 meters in 3 seconds. I'm looking at 181 meters per second was the blast speed of the cannon. Okay. Well, it says the horizontal component of velocity for the entire flight, which therefore would also be the velocity of the cannon because it was aimed horizontal. Okay. Boom, right there. All right, good to go. Okay, you guys get that? Okay. All right, so in this case, I started with vertical because I had a bunch of information stacked up there, but you know, sometimes you start with the horizontal. Right. Depends on what information you have. 53. Okay, now we're moving to Unit 2, dynamics, forces, Newton's laws of motion. There's some friction involved in this one. What is the coefficient of kinetic friction between the block and the surface of the incline that would allow the block to slide down at constant velocity? This was a lab you guys did. This is straight up a lab answer. Okay? I'm going to solve this one in terms of variables. But let's do the full free body diagram. This is a really good opportunity to review free body diagram for this one. So we got an incline. Right. If you guys are following along in your notes, see if you guys can draw the free body diagram before I do. All right, you should definitely be able to, right? Midterm question, right? Should have gotten it right then. All right, so here's the block. Right. We'll switch over to let's do peak for the force vectors. Right. This thing has a weight acting straight down. So I'll label that mg for the weight. What other force should I put on here?
Normal force.
All right, normal force. Yeah, I like normal force. Okay. There's a specific length that the normal force has to be. Kind of get back to that moment here. Okay. And what's are there any other forces?
Frictional force.
Friction force. Okay. There's also a specific length that the friction force has to be for this particular scenario. So try to get that about right. Okay. All right. So you guys came up with that, right? You guys came up with the rotated Cartesian plane, the whole deal. Okay. Now these two forces are aligned with that Cartesian system, okay? But not the weight. So should we split the weight into components? Yeah. Now here's where it's kind of an AP thing. You don't want to make these solid because you would be like double counting that vector. Right? Either you want to just like imagine them being here, like use your imagination. Maybe bring your limiting pen, or if you dash them. I've talked to AP graders like, hey, students dash them. We'll go ahead and get a little points, but I want to be careful about that. Okay. So what's this component right here equal to? Mg sine theta. There you go. Okay, so this one must be mg cosine theta, right? All right, you guys remember this? Okay. And what we've done effectively is like replace the weight in terms of its components. Okay, so now we got kind of these four things going on. Sorry. Okay. Okay. Now I said the block is sliding down at constant velocity. What does that mean? That means the block is in a state of equilibrium. Equilibrium. Because at rest or constant velocity, those are both equilibrium. The forces have to sum to zero. If the forces sum to zero, doesn't that mean not only is this equal to this, which probably figured out, but also this is equal to this. Right? That's what equilibrium is getting, right? The forces have to sum to zero along each axis. And so if this is an FRQ, if you said this, some of the forces, along each axis equal to zero. Complete phone call. Okay, pause. All right, recordings resumed. All right, so I can say, for example, friction force must be equal to mg sine theta. because of equilibrium, because sliding down constant velocity, it's true specifically because of that. But you guys know another formula for friction force. Friction force is also equal to what times what? And it's near the top of your AP equations. Yeah, coefficient of friction times the normal force. Now this is true specifically for a coefficient of kinetic friction, and if it's sliding, it would be that one, right? Versus static friction, right? Now your equation says less than or equal to, because if it's static, it could like build up to that point. But if it's kinetic, you just say equals. Okay. Oh, and normal force. Well, that's your mg cosine theta, isn't it? Right? So friction is equal to this, friction is equal to this, and your normal force is mg cosine theta. Right? Think of this kind of like a three-way like system of equations, right? You make a bunch of substitutions, which we're about to do right here. No, switching color. How about that? Right, so we got right, but this mg sine theta, that's friction force, right? Mg sine theta is equal to this friction, coefficient of friction times normal force, but normal force is mg cosine theta. Okay. We've done this several times in this class, right? So you guys should be pretty comfortable with this. Okay. Okay, now the question is, what is the coefficient of friction? That's what we're solving for. Okay. What cancels out of both sides?
MG.
Yeah, the weight of the block, right? Both the mass and the gravity field of the planet, right? As long as you have gravity, as long as you have mass, it doesn't matter what the magnitude is. Okay? Right, so can I divide the cosine over and get coefficient of kinetic friction is, oh guys, what's sine divided by cosine? Tangent. Boom. Okay. You guys did a lab. You guys remember like taking? I think I had you guys either take a textbook for your desk and like angle it until it started sliding down. You can figure out coefficient of friction with nothing but a protractor. Where's my? I want it here for visual. Okay. This is all you need to figure out coefficient of friction. Just this tool. You can figure out the whole thing. I think it's been an AP question before. What do you need to figure out coefficient of friction? Okay. So use a protractor. Do the whole thing. Okay. Tangent of the angle. So let's say right. I mean, I told you the mass of the block too, but it cancels out. So, okay. So tangent of my angle says 29 degrees. I'm saying 0.55 is the coefficient of friction there. Yep. All right. Okay, so tangent of the angle. Okay. Next, straight off one of your labs. Okay, number 54. All right, so this also looks like a unit 2 dynamics question. What is the tension in each cable? Right, so really classic physics question here, like especially if you're going to be an engineer one day, like designing buildings and bridges and stuff. Guy in number 54. Oh, so 54. All right, we got this type system going on. All right, we got here. I'll say this is the point where everything comes together. Okay. So I gave you guys. Oh, actually, I just told you the mass, didn't I? Yeah. Okay. So mass times gravity field would be the weight. Right. So whatever the mass I told you was, you have to multiply by about 10 meters per second squared to get the weight. Something like that. So if I said it was like 15 kilograms, 15 times 10 is 150 newtons. Right. Right. And then a couple of ropes going up. There's one this way. There's one this way. Trying to get this kind of to scale here. Right. And it's the same angle here as here. It's the same angle, whatever that was. Okay. Right. Now, wouldn't it be true? There's two conditions. In the x direction, the forces have to sum to 0. In the y direction, the forces have to sum to 0. Right? Because we've got like a two-dimensional setup. Right? Don't worry about torque. You just focus on those two. Okay. That. Okay. All right, so I'm going to split these guys into components. Now I could go up and over, or I could go over and up. I'm going to go over and up just because I got a little bit more space in the paper to work with. Okay, so split these into components. Oops, should have dashed that a little bit better. Those are dashed, right? Dashed components shouldn't look solid at all. Probably count off for that. Okay. All right. Ooh, that angle. Is that angle? It's the same angle, right? Okay. So whatever the tension is, call it F sub T. Right, we're trying to solve for the tension force. What is that tension force? I know this is F sub T sine theta. This is F sub T sine theta. Well, one's positive, one's negative because they cancel out. right? That satisfies the top condition. Okay? And then the vertical parts, isn't this f sub t cosine theta? And this is also f sub t cosine theta, right? Wouldn't that be true? Right? And it wouldn't be true that the cosine components added up is going to balance with the weight down.
We're dismissed from the gym about 10 minutes ago, so they should be getting to your classes within the next couple of minutes. Just so you're aware, seniors are heading back to their classes now. Thank you.
Right? Wouldn't that be true? Okay. So look at that. Let me say 2 times the tension force times cosine theta has to balance out with the weight. That'd be true, right? Okay. And the question is, what is wait, is that the angle I gave you guys? That right. Okay. What is the tension force? What was the question, right? What is the tension? Okay. So it should be weight divided by 2 times cosine of the angle. You like that? Okay. Let's check that out. Sure, got that right. Okay, so I have 85 kilograms at 29 degrees. So if I go 85 kilograms times 10 meters per second squared divided by 2 times cosine of 29 degrees, I'm getting 486 newtons. Oh, there's 486 newtons. Okay, so we're good. Okay, so let's hit it one more time. Free body diagram, split the components to align with the system. This bottom condition, some of the forces of the y goes to 0. These two going up, these 2 components up have to balance with this weight down. This was also straight off a lab you guys did. You guys remember breaking out spring scales and making exactly this configuration, the whole deal. Okay. Okay, so these 2 have to balance with this one down. That's exactly what this says. Okay, those 2 up have to balance with that weight down. Okay, solve for the tension force, algebraic rearrangement, boom, done. Tell you what, sort of a shortcut if you want to play off a multiple choice. What if these 2 were exactly vertical? Wouldn't each strand therefore be half of the weight? Right? And the fact that they're not exactly vertical or spread out into like a Y shape means it has to be a little bit more than half the weight for each one. So if I use that as a good tip, I know the weight is 850 newtons. Divided by 2 would be 425 newtons. I say, well, it has to be more than 425. Right? In this case, it was at 485. Okay, so we're good. Okay, so all right, so that was unit 1, unit 1, unit 2, unit 2. Okay,
Part of the interruption, could the Eastern Florida Bridge to Success students meet in the front of the school, please, and thank you.
yeah, go ahead. Yeah. So if anybody's got a club photo, yeah, go ahead. All right. Next one was straight from unit 7. I tried to put these kind of in order, but just how lay out on the page. So unit 7, which you guys had just taken the quiz on. In fact, this was almost identical to one of your quiz questions, which almost everybody got right. So thought you guys would do pretty good on this one. The only difference from your quiz was I changed it from a basketball, which is a spherical shell, to like a solid ball. That's the only difference. So you give this thing a kick, and it spins on your finger. And the question was, how fast does it spin? And this was conservation of angular momentum, right? Sorry, it was I should say angular impulse. You guys know linear impulse change in linear momentum is mass times change in velocity. Is that true? Well, and it comes from applying a force for some time interval, right? Which comes from applying a force for some time interval, right? You guys could have said that. And we're just doing the rotational version of this. So the change in angular momentum is equal to I times change in angular velocity, which comes from applying a torque for some time, right? Straight off your quiz, right? You guys have just been quizzed on this. Okay. Okay. So we're trying to figure out, well, it says final angular velocity, but if it starts from rest, then this would just be omega, right? Okay. Couple substitutions here. I told you right here in this box was 2/5 mr squared. That's true for a solid sphere. You don't have to memorize that. If AP wants you to apply that, they would give that to you, okay, which they might. Okay. So in place of this I'm doing 2/5 mr squared. Okay. Is it delta omega? I'll just call it omega because it goes from 0 to some omega. So omega final. Okay. And torque, well, isn't that r cross f? R cross f. Right, and then for some time interval. Right. So you have all those bits except for omega. It's going to solve for omega. Okay. Let's get in terms of variables. On the r's cancels. Omega is equal to, okay, I got a force for some time interval. So I have to divide this mass and a radius down. And then 2/5 is going to multiply to become 5/2. Okay. Oh, I remember I asked you guys on your quiz, and I had you guys solve it in terms of variables. So the only difference was you had a basketball on your quiz, so I think it was 3/2 instead of 5/2. So you guys already had the answer in terms of variables. You just feed in the numbers, right? Right? You guys can do it. All right, next one. These three went together. They had to do with this guy swinging on a vine, okay? Which we did plenty of these. So there's a little bit of a conservation of energy, unit 4. There's a little bit of unit 3, centripetal force going on. All right, yeah. All right, so we got this guy swinging on a vine. So let's review this whole thing. Got it. All right, some length of a vine. Now the vine itself has negligible mass. I wrote that, hand wrote it up here. Okay. So all the mass is in this guy swinging. So I'll give him some mass m. Right, length, angle. It's gonna swing. Right. Now you guys just figured out experimentally that the time period of that swing has nothing to do with this angle, but that's not where this question was going. Okay. That angle does matter for the maximum speed, which is the speed right at the very bottom. Okay. That was the question. Yeah, that was the question. How fast is he going right at the very bottom here? What is here? I think that. So I'll call this V like V max, but speed, right? Okay. So you can solve the conservation of energy. Okay? And I know I made a big deal about doing this in the midterm review with you guys because this is a really classic. You should be able to do this for this, right? And so is this right here L cosine theta? So this must be L minus L cosine theta, right, which is equal to, if you like, you can factor an L out. You don't have to, right? But you could. Right. So that's the height change. That's the height change right there. Right? Can I do conservation of energy? Sum of energy initial equals sum of energy final. In fact, if this was an FRQ, which this would be a pretty solid FRQ question, I bet if you just wrote that, you would get a point. You say, oh, hey, what's that? What kind of energy here? Potential energy, MGH, gravitational potential. What kind of energy here?
Kinetic.
Kinetic, 1/2 mv squared. Boom, boom. Okay. Oh, you guys know V is going to be the square root of 2gh because you guys have seen this so many times, including the midterm review. We did that lots of times. And that h is this expression right here. 2g L 1 minus cosine theta. Okay. So if you feed in the numbers they gave you, gravity field of the earth, the length of the vine, the angle, hit the maximum speed right at the bottom. Okay. So I should be able to do that. Follow-up question. What is the tension in the vine at the bottom of the screen? Okay. Let's do, this kind of reminds me of my quiz questions from yesterday, the one I helped you out with a little bit. Okay. Let's look at his free body diagram right at the bottom of the swing. Right. So 2 force vectors, weight down, mg, and the tension force in the vine pulling up. Right. Which force is bigger? The tension force. S of t, tension force. And it's bigger because he's on a curved path. There must be a net force because he's accelerating. It's centripetal acceleration, right? Okay. Isn't it true that F sub c, centripetal force, is the net force, which is the tension minus the weight? See, if he was just hanging at rest, the tension would be equal to the weight. But the fact that he's in motion with some speed, right? There's going to be like more tension than weight. And centripetal force, you guys know, is mv squared over r. Okay. The question is, what's the tension in the vine? Rearrange this algebra. Wouldn't it be like this? That would be true, right? Yes, yeah. Okay. And here's now, if this was an FRP, you'd have to show that whole process. Might be like point. There might be several points, one at a time. Okay. Here's kind of a shortcut way to think of this. Okay. If he's not moving, if that v is 0, then the tension would just be equal to the weight, right? Okay. But if he is swinging, if he's on a curved path, then the tension of the vine is instead the weight plus the sort of like the centripetal effect. You can kind of think like that. You just add it on, you just tag it on. You see that? Right? Kind of a shortcut to get to the answer. Okay. You see that? Okay, all right, everybody good? All right, next one. Let's see if we'll put this one in before the bell. Number 58. Alan's friend Bob, who is more massive than Alan, swings on same vine, or same length, same starting angle, blah, blah, blah. Right, same gravity field. It's kind of a double question here. What is Bob's maximum speed compared to Alan and the maximum tension in the vine? Right? So really I'm saying if you change out the mass. Well, let's go back to max speed. Guys, does max speed have anything to do with mass? No, it cancels out right here. So it's the same speed, right? Same speed. Right? We're assuming a math with vine and it makes a little difference, but okay. Same speed. And the maximum tension at the bottom, oh, well, that does depend on mass, but it's directly proportional to mass. So if Bob is twice as massive, then the tension is also twice as massive. You like factor in them out. Okay, you guys get that? All right. You guys have a great weekend. We'll hit these last two sometime next week and continue on with review. All right. See you guys on Monday.